Hello, I would like to welcome you to this group's presentation on antennas. EE2FH3, Group B23, David, Susie, Ahmed, Ishmael, Nicholas, Brendan. We're going to start off with a quick outline of the contents of this presentation. We'll begin with a brief introduction into what our group has put forward, and then go into some of the application and theory behind antennas, followed by our actual applications that we are looking at to use with these antennas, and then go through some of our simulation, how we plan to simulate it using OpenEM, followed by a quick overview of our project organization and a brief conclusion. So to introduce, this project has been given to us to research, simulate, and design an electromagnetic structure, and use simulations using the OpenEM software. And in the end, the plan is to move from a basic knowledge of antennas to an expert knowledge to the point where we can actually apply it to a real-life scenario or problem. Antennas are used to transmit and receive electromagnetic signals in the form of radio waves. And by using a broad spectrum output, it's possible to jam local signals. And this is what our group has focused on mainly as far as application.
Okay, so I'm going to talk a little bit about how antennas work and the physics behind them. So the basic principle about antennas is they convert electromagnetic power into radio waves. They use metallic conductors to connect to the receiver or transmitters. In our case, we're going to be looking at creating a transmitter. This is because we're looking to design the antenna for blocking a specific signal, such as cell phone frequency. There's two main kinds of antennas. There's omnidirectional and there's directional antennas. We're going to be looking at creating an omnidirectional antenna as well, just because we want a signal that projects in all directions, while a directional antenna would actually only focus the beams in one specific area. So I'm going to talk a little bit more about the magnetics behind them. The gain varies based on the design. This usually refers to the wave density per unit angle. Creates an oscillating current of electrons to create the magnetic field. So basically, you're going to have electrons moving and fluctuating, and this movement of electrons is actually what's going to create an electric field, which allows the antenna to do the work.
The main issues with cell phone jammers are legal issues, safety issues, and health issues. For legal issues, cell phone jammers are illegal in most countries, especially developed nations, and some countries can consider it illegal to use, buy, sell, or own them, while other countries, depending on the country, some may allow them to be used in prisons, some in government agencies, some in office buildings, or sometimes in schools as well. And in Canada, they are illegal except by federal law enforcement agencies who have obtained approval. And the reason that cell phone jammers are illegal is because a lot of countries consider them property theft, and that's because private companies have paid for the rights to use certain frequencies, and if you jam those frequencies, it's as if you're stealing their property. And for safety issues, the cell phone jammer will block all signals, not just unwanted ones, so it can interfere with emergency lines, and as well, it can make someone unable to call out for help in dangerous or emergency situations. And finally, health issues. So the antenna in the cell phone jammer emits electromagnetic waves similar to the ones that a cell phone would emit, and prolonged exposure to this radiation can cause serious health risks, especially if you're using it in close proximity. So for example, if you had a cell phone jammer in your car, it could be very dangerous because you have it so close to you so often. And mainly, these risks include an increased risk of cancer. And in extreme cases, radiation exposure has been known to create an electric shock in the body. So those are the health risks involved in using a cell phone jammer.
Design and simulation. Antennas operate around a certain frequency, which means each antenna has a specific function or specific use so as not to interfere with other RF waves. There are many parameters that must be considered when designing an antenna. So for mounting an antenna on a car, for example, If you're using a magnetic mount on the trunk versus a magnetic mount on the roof, that gives you a different gain. For the purpose of this course and this project, we'll only focus on bandwidth and directivity, which I'll talk more about in details in the next few slides. So bandwidth, as mentioned before, antennas operate around the resonant frequency. And the bandwidth is defined as the maximum frequency minus the minimum frequency. So if you look at this diagram here, the center frequency or the resonant frequency is here, and the bandwidth would be f2 minus f1. So for a frequency range of 90 to 95, our bandwidth would equal to 5. In North America, cell phones operate at around 1.9 gigahertz. So the output of our antenna for a jammer would have to be in that range. It'll have to be around 1.9 gigahertz. Other example frequency ranges include for AM radio waves 30 to 300 kilohertz, and for underwater communication 3 to 30 hertz. Directivity is defined as the ability of antenna to focus its transmitted waves. So you can think of it, it's analogous to a spotlight versus a regular bulb. A spotlight focuses its light on a person, whereas a light bulb, for example, in a room, shines light everywhere inside that room. So the typical shape of the transmitted waves will look something like this, where you have your main lobe, which is where the majority of the transmitted waves are. Then you also have your half power points. This corresponds to the 3 dB line, which is shown on the previous slide over here. So when considering directivity, we want to focus most of the waves in a certain direction. So we want the main lobe to be bigger, and we want to minimize the back lobe. So for example, if we're mounting the jammer inside a classroom, we want to focus most of the waves inside the classroom and reduce interfering with people, for example, in the hallway. Directivity also depends on the location and placement of the jammer. So after taking into consideration all these parameters, the antenna for the jammer we're designing will be simulated using MATLAB and OpenEMS.
Alright, we'll move on to talk about some of the various applications of antennas. To refresh, an antenna is a device that converts electrical signals to radio waves and vice versa. A basic application of this function would then be general wireless transmission. In fact, this is one of the very first uses of antennas, which included reproducing basic electrical signals and audio signals wirelessly at a receiver such as a phone or a radio. On the next slide, we move on to more applications of this concept of wireless transmissions employing radio waves. Such examples include remote controls. Now, rather than a simple send and receive transmission, there's an array of signals, each controlling a different aspect of a device. You also see antennas implemented in GPS receivers, which receive wireless signals from GPS satellites and use that information to calculate the location of the receiver. Similar to a GPS receiver is the radar, which uses the reflection of emitted waves to determine the location of surrounding objects. Now we'll talk about some unique applications of antennas. The radio frequency identification, or RFID tag, is unique in that it's very small, so it can be placed virtually anywhere and it doesn't require an internal power source. It can use the radio waves it receives to power itself and transmit back information. On the side here, you can see just a small diagram of what an RFID tag looks like with antenna included. We'll now talk about wireless signal jammers. And these take advantage of the fact that electromagnetic waves interfere with each other. They emit a radio wave at the same frequency of the target signal, so that the signals can destructively interfere, thereby jamming the target signal. You can see also a picture of what a common signal jammer looks like for a cell phone. These are just some of the many applications of an antenna. For a device that can convert electrical signals to radio waves and back again, the possibilities are almost limitless.
I will be talking about the project organization with regards to our project. And so I just created a Gantt chart to record our our progress, and keep up to date with our project. So I have us starting the 5th of February, relatively close to where we were given the project. And we just wanted to establish a subject, find information on that said subject, and make a schedule for future events. We also wanted to establish a problem statement for Dr. Bacher. And then the February 17th, we wanted to find more technical info on it and find some info on the exact design specs for our project. We also wanted to look into some circuitry for the device, and creating and submitting the YouTube video was pushed to a further date, and so we kept that in consideration with our project as well. By February 26th, we wanted to start using OpenEM and start looking at some tutorials and go through some simulations of possible antenna simulations. And we want to really implement our model, and we want to start searching for patents. By the 5th of March, we want to expand specificity of design constraints and really identify the weaknesses of our current project and hopefully find alternatives. We also want to search for even more patents to enhance the legitimacy of our project. By March 19th, we want to prepare a presentation and really look into the all-around effect of our product, and look into the device legalities and reflect on the project, what we could have improved, and what are some other alternatives we could have considered. And by April 2nd, we wanted to submit and present a video and hopefully, for bonus points, build the device itself.